What's up guys, Jackson here. The TAs, we are making a post-exam 3 review for you guys just because we didn't have recitation, we didn't have time to go over the tests. So the test average on this was definitely a little bit lower. It was a hard test, but just words of encouragement going forward. I do think, definitely with test 4 in the final, there's a lot of ground to be made up. It's worth almost 50% of your grade. So um, if you're not sitting in a good spot right now, work really hard to finish the semester, and you can definitely finish strong and do well still in the class. On top of that, there's a very generous curve. So just keep the morale high and keep working hard. The other thing, if that's not enough for you, I have the salad business. This is our Instagram, Drizzle Salads. And I put a promo code on there just for people in the class. It's $4 off. So ace the final. When we open it up in like 2 weeks, we're doing a salad December 10th. You use the code and get some discounts. So anyways, I'll go to question 1 of multiple choice. Okay, question 1. First thing you're going to look at when you're naming a compound, the question was to name this compound, is what is the parent chain? This is a cyclic structure, so we have cyclohexanol, 1, 2, 3, 4, 5, 6, as the parent here. So we have this is going to be the main priority group, the alcohol, and so rather than have it be cyclohexane, it's going to be cyclohexanol. Okay, from here you're looking, if this is the number 1 carbon in the chain, then from there, where do you go for naming? And you would go here before here because this is the soonest branching point. So you go 1, 2, 3, 4, 5, 6, and you're back to where you started. So when you're naming it, the first substituent is the methyl group, and the other substituents are these on the 5th carbon, the other methyl group. So that would be 2, 5, 5, trimethyl cyclohexanol. Question 2, rank the following in order of increasing boiling point. So the first thing you're going to look for is intermolecular forces for the boiling point, and the second thing you're going to look for is surface area. So with the different forces in these molecules, they all are going to have hydrogen bonding, but this one is going to have more hydrogen bonding in that there's the 2 different ones. So this you would think is going to have the highest boiling point. So this would be 1. Okay, then we're looking at differences in surface area. This also has a larger surface area. It's spread out. These ones are more compact. This one is also spread out. So this would have the next highest boiling point because of surface area. Okay, then we're looking at between these two. This one will have more surface area than this one because this one is more compact. The alcohol is on this carbon that is connected to 4 things, whereas this is a 2' alcohol versus the 3' alcohol. So this would be the 3rd and 4th. So highest boiling point, lowest boiling point. Okay, question 3 was you were given this reagent, the H2SO4, and it was asking what products you would get. So this mechanism, basically, this alcohol is going to be converted to the better leaving group is going to be converted to water, like that. Water can then leave, and you have this carbocation here. So from this point, this base, the HSO4, can then it can then take a hydrogen from here, whoops, forming an alkene, forming this product. Okay, but another situation, another thing that could happen, and this is the part of the problem that's important, is that this alkane in this position, it can rotate. Any of these bonds can rotate. Once it's locked in the alkene, this is a trans conformation. But before this ever happens, you could have this basically looks something like this, where you have it arranged like that because this bond can move however it wants. And when this base comes to grab the hydrogen and makes this, you would be left with the same alkene, but it would be in a cis conformation. So either of these products here both could result from this reaction. Question 4 had to do with this reaction with HBr. So basically what would happen, like in question 3, the mechanism is going to look like this, where this alcohol is converted to a better leaving group. So it's converted to water. Okay, so you have this. At this point, the water can then leave, which gives you an intermediate that looks like this, where you have a carbocation intermediate. Now, the reason that the question was asking about the products, and one of the answers was a racemic mixture. The reason that the answer is a racemic mixture is because this bromine can add either above or below. So whenever you have this carbocation intermediate and it's attacking, you're going to end up with a racemic mixture. So you have the bromine can add either as a wedge or a dash. So your products are this and that. Okay, question 5. So this one's asking for which of these would a carbocation rearrangement? So looking at this first one, if you were to do a rearrangement, let's say you do a hydride shift from here, and you shift it over, then you would be left with this, which is just the same thing. So it's not something that is likely to happen, because a hydride shift would happen so that you can get a more stable. So let's look at the next one. There's obviously a lot of branching here, so you can't do a hydride shift. This is a carbon connected to 4 other carbons. But you can do a methyl shift. If you shift this over here, you are left with something like that. And in this case, that would be more favorable to have the positive charge. So this one, yes. This would do the rearrangement. This one, no. Okay, this last one, yes, if you were to hydride shift from this spot, then you are left with carbocation on the more stable intermediate. So 2 and 3, yes, they would do a rearrangement.
Alright guys, so let's go over number 6 from the multiple choice. So looking at this, we have a secondary alcohol that's reacting with POCl3, or POCl as we call it. So for this one, you don't have to draw out the mechanism, but I'm going to just because it will help us understand a little bit better this problem. So first thing that's going to happen, the lone pair on the oxygen is going to attack the phosphorus, taking off one of these chlorines. Which is going to form this intermediate right here. Okay? So once we get here, our pyridine is going to come in and it's going to deprotonate our hydrogen. Okay, so what we've done here is we've taken our OH group, our alcohol, which usually is not a good leaving group, and we've converted it into a good leaving group using POCl3. Okay, so this is now a good leaving group. So when we have a secondary alcohol with POCl3, it's going to do an E2 reaction. Okay, so that's something that you needed to know from knowing all those reactions and be able to recognize that it's going to perform an E2 reaction. So when we do an E2 elimination, this one was a little bit tricky because lots of times what we think is we want to form the more substituted alkene, which is generally true because the more substituted alkene is usually the most stable. In this case, however, we cannot form the more substituted alkene, which would be okay, so we can't, I guess this would be gone. We can't form this. And the reason why, the reason why is because if you think back to the last unit, we talked about how you have to have hydrogens that are anti-periplanar to your leaving group when you're performing an E2 reaction. Remember what anti-periplanar means is that your leaving group and the hydrogen that you're taking off, they have to be in opposite planes of the page. So we looked at some of those sometimes with chair conformations and whatnot. The reason why is because if you have your leaving group sticking up like this, usually has a lot of electrons, and then you have your hydrogen you're trying to steal down here like this, it's good if they're opposite, but if they're in the same orientation, if they're both up, or if they're syn periplanar, then when your base tries to come in to take your hydrogen, there's electron repulsion between the base coming in and your leaving group. And that can't happen, okay? So right here in this case, we have a hydrogen, right here, we do have a hydrogen. However, this hydrogen is on a wedge. And I forgot to draw it in here, but our leaving group is also on a wedge. And so when our base comes in, right, which is still pyridine, okay, when our base comes in, if it were to try to take this hydrogen right here, it's got a lone pair, so it's got a good amount of electron density to it. If this comes in, it's going to repel. There's lots of electrons here with these chlorines, these oxygens, and these two are going to repel each other. So it's not going to be able to come in and take this hydrogen because these are both wedges. They're in a syn periplanar conformation. So that is why we cannot form this as our product. That's why option B is incorrect. So that only leaves us with one other option. If this is our leaving group right here, we have a hydrogen here, we can't take that one, and we have two hydrogens right here. Okay? One of these hydrogens is going to be a wedge, and the other one is going to be a dash. So think to yourself for a minute, when this pyridine comes in to take a hydrogen, which one is it going to take? It's going to have to take the one that's a dash going into the page. So this lone pair will grab this hydrogen, and the electrons from this bond will go right here, kicking off this oxygen. Right? And all this is our leaving group. So that will leave us with this as our product, which is option A. So that one was a little tricky. You had to recognize the anti-periplanar now. Alright, let's take a look at number 7. So number 7 on the multiple choice says, what products are obtained in the reaction of methyl phenyl ether with excess HBr? So the first part of this problem is you need to be able to recognize, or you need to be able to know, or be able to draw the structure of methyl phenyl ether. And I know we didn't talk a lot about the nomenclature for ethers, but you did need to know what we did talk about. And so this would be the structure for methyl phenyl ether. Remember, an ether is something that has an oxygen in the middle and then an R group on either side. In this case, methyl phenyl ether tells us that one side has a methyl group, the other side has a phenyl group. Okay? And if you didn't know what a phenyl group was, by looking at the multiple choice options, hopefully you could have figured out, if you knew enough about the nomenclature of ethers, you could have realized that this is going to be a phenyl group. Okay? So first thing that's going to happen when we have an ether with a strong acid is that the oxygen is going to be protonated by the hydrogen on the strong acid. Like so. Okay? And then that'll get us to here. Okay? So here's where we get to next. We have a positive charge on the hydrogen and still our phenyl group and our methyl group. Now, usually when we get to this point, let me just pull up another example. You may have seen something like this before. And usually with something like this, when we get to this stage where it's protonated and it has the positive charge, we would usually look at these two sides and say, okay, the more substituted side will come off first. And so we would say that this, our oxygen with the hydrogen and the methyl group, which is kind of like water, right? Oxygen with two things attached to it and a positive charge. Usually we would say that this would come off as our leaving group, and then this would be on its own as a tertiary carbocation, and that this would proceed, this part here would proceed via an an SN1 reaction, where this comes off by itself, and then you have something else coming in to substitute. Okay, so that usually is what we would see. In this case, this one is a little bit tricky as well because you might have looked at this and thought the same thing. However, recognize that this right here is an aryl alcohol. So we talked about how vinyl, we talked about this with halides, but vinyl halides and aryl halides are not reactive when it comes to substitution and elimination. And so for these examples right here, like I said, we talked about it with halides, but the point is that these carbons are not sp3 hybridized. In this case, they're sp2 hybridized. They need to be sp3 hybridized to undergo an elimination or substitution reaction. So that's why for this one right here, this side cannot do what we would typically expect because it is an aryl alcohol. And so it cannot do an SN1 reaction. So because of that, the only other option is for the other side, the methyl group, to react. And for the methyl group to react, kind of same thing. Instead of looking at this side as our leaving group, we can look at these two, this side, as our leaving group. Because this is only primary, we don't want to do SN1, because if we did SN1, then we would be creating just a single carbon by itself with a positive charge. All right, that would be if this came off in one step. So we don't want to do that. Instead, it's going to proceed via an SN2 mechanism. And remember, we have our bromine from right here that came off. And so this bromine is going to act as a nucleophile. It'll attack right here, and then this all acts as a leaving group. So that's going to come off. And then we're left with sorry, that was a really bad hexagon. Okay, we're left with these two options. And so that would be answer A. Okay, so this one was a little tricky. You had to recognize that because of the aryl alcohol, it would not react like you typically would expect it to, with the more substituted side coming off first. Alright, let's talk about number 8. So number 8 is talking about boiling points. And when we talk about boiling points, we want to focus on intermolecular forces. Okay? So if you remember, think back to when we talked about this before. We talked about it a little bit with alkenes in this unit. But when you have molecules, if they have strong intermolecular attraction, then when you're heating them up, it's going to take a lot more energy to break them apart. Whereas if they have weaker forces between them, then you won't need to boil it as much, you won't need to heat it up as much for those molecules to all break apart. Okay? So looking at these different options, we want to look for intermolecular forces. They don't really have any functional groups like we were looking at in Unit 1. They're all just alkenes with a double bond in carbons and hydrogens. And so looking at these, a key thing to recognize is that this one here and this one here are both going to have pretty strong dipole moments because of their orientation. So if you compare these two to each other, they both have the same number of carbons, I think, and they both only have one double bond, but because of the orientation of this one, it's going to have that dipole moment. Okay, well this one also does. So to determine between these two, we need to remember that, so we're talking about dipole-dipole interactions here. Another intermolecular force is our van der Waals forces. For van der Waals forces, we want something that has the largest surface area. So even though these two both have the same number of carbons, this one, it's more spread out, more stretched out, and so it's going to have a higher level of van der Waals forces, which will make it stronger than this one. Now this one here, it does have a lot of surface area, so it is going to have high van der Waals interactions, but the van der Waals interactions will probably be pretty similar to this one, but this one also has the dipole moment to it. Alright guys, let's look at number 9 on the multiple choice. So number 9 says, which of the following occurs during the addition of HBr to propene? So once again, this one you do need to know a little bit of nomenclature. Fortunately, Dr. Castle doesn't make us dive too deep into all the intricacies of nomenclature for some of these recent units. But you do need to know that propene is, so remember propyl is 1, 2, 3 carbons. And propene, because there's no numbers with it, like 2-propene or something, we know that it just starts at carbon 1. However, also it's a propene, so because there's only 3 carbons, it could only be here or here for a double bond. So that makes it a little bit easier. Okay, so we're adding HBr. Okay. So what's going to happen here is the electrons in the double bond are going to be protonated by the hydrogen. And so we have two options. We can either put the hydrogen right here, and that'll give us a positive charge right here, or we could add the hydrogen right here, and that would give us this, okay? So I say there's two options. In reality, there's only one option. According to Markovnikov's rule, the hydrogen will go to the less substituted carbon, and the positive charge will go to the more substituted carbon. The reason that we want this to happen, or the reason why this happens, is because it's the more preferable pathway energetically, because a positive charge that's disubstituted is a lot more stable than a primary positive charge, okay? So this will not happen. Alright, so that's going to add, then we have this. Once we get this here, our bromine from over here, which I forgot one of my arrows. Okay, you can dock me a point for that. The bromine is then going to add to this positive carbocation right here, which gives us this as our final product. So if I were you and I was doing this question, when I see this, I would just draw it out first, draw out the reaction mechanism with the arrows, even though you don't have to for the question. And then once you have it drawn out, look at the options, okay? So option says, once again, right, which of the following occurs during the addition of HBr to propene? A says attack by Br minus on the alkene. So that's saying that bromine is attacking the alkene, okay? So bromine is going to attack, but it's not attacking the alkene with the double bond, it's attacking the alkane once we have the positive charge, okay? So that's not true, so A is out. that one could be easy to miss, right? Because if you don't draw it out, you might think, oh yeah, bromine's going to attack. But be careful, okay? B says formation of a bromonium ion, okay? So the bromonium ion, that's the kind of thing when we form like the ring. Right? When we have something like this with a positive charge, that would happen if we're reacting an alkene with either Br2 or if we were reacting it with Br2 and H2O, and that's when it does that thing where, right, it goes like that and it forms the bridged halonium ion. But that's not what's happening here. With just HBr, right, it's getting protonated by the hydrogen. Okay, so it's not B. C says formation of a primary carbocation. So we talked about that. That would be if we added our hydrogen here and our positive charge here. We don't want to do that. According to Markovnikov's rule, we're going to add, and this is what D says, right? We're going to add our hydrogen here and form a secondary carbocation. So D is the right answer for that one. So let's look at number 10. Number 10 shows us these different alkenes, and it asks us which alkene will react the slowest with HCl. Okay? Now, when you first see this question, you might think, wait a minute, maybe I know how to react that with HCl, but how do I know what's going to be slowest? We didn't talk a lot about, well, this one will be fastest or slowest, okay? So this is a good example of a question that ties in concepts we've talked about in previous units with something in this unit, or the most recent unit, okay? So remember, when we're talking about rates, or how fast something proceeds, what determines the speed of a reaction? Hopefully you can think back to Unit 2, the last unit, where we talked about how the rate determining step is going to be, right, the step that determines the rate. It's going to be the slowest step. We also call it the slow step. And we also say that the energy of activation will determine the speed of a reaction, the speed of that first rate determining step. Okay? So if we were to look at an energy diagram, right? This is just a simple example. Maybe it doesn't correspond to this question, but here's our energy of activation, and however big or small this is, this rate determining step will determine how fast or slow the reaction proceeds. Okay? So looking at these, if we wanted to, we could react all these with HCl and see what it would look like. So I'm just going to do that really quick. For this one here, we would add hydrogen. And for this one, it's going to be really important, right? Know your mechanisms, like we've gone over, and also know Markovnikov's rule, which we talked about in the last problem, but it tells us that the hydrogen will add to the less substituted carbon, so that the positive charge will form on the more substituted carbon. So for this first one, our hydrogen is going to add here, which will give us this carbocation. And then our Cl will add in to the positive charge. Okay. With this one, similar thing. Our hydrogen is going to add to the less substituted side. We'll get this carbocation. And you can skip ahead if you don't want to see me draw all these out. Okay. Okay, now this one, right? Hydrogen's gonna add here, so that our carbocation will be more substituted. Going out there. Okay, now for this one, hopefully you guys can see that, yeah. For this one, it's symmetrical, okay? So it doesn't really matter if the hydrogen adds to one side or the other. Either way, the carbocation will be on a tri-substituted carbon. Okay, like so. So remember, the main thing here is where are we putting the carbocation? So if you'll remember, when we talked about forming carbocations, forming a carbocation is going to be our rate determining step, or the slow step. Because more than anything else, it's the hardest thing to do in the reaction. So imagine like each step of the reaction is a little hill that you have to climb up. And forming the carbocation is like going up a really steep hill. It's going to be the hardest thing. It's going to take you the longest to climb up that steep hill. And so it's going to be the rate determining or slow step. So these all have a similar slow step in that they're all forming a carbocation. Now what we want to compare is which one of these different reactions is going to form the most unstable carbocation. Because whichever one forms the most unstable carbocation is going to have, so right, if we were to draw an energy diagram, I'm not going to draw exactly what it would look like with all the steps, but for our first step, or the step where we're forming the carbocation, maybe, let's say, I guess it would be the second step. Remember that this is energy when we look at something like this. So let me just put a disclaimer. You don't have to think about energy diagrams to understand this question. I'm just going to throw this explanation in here if it helps you. If it doesn't, it's okay. You can ignore it, okay? So looking at energy diagrams, energy goes up along the y-axis. So that means that something here is kind of stable, this is unstable, this is more stable, right? And so for this step, when we're looking at our intermediate of our carbocation, if we make this carbocation really stable, let's say that it's a tertiary carbocation, what's that going to do to this hump? It's going to bring it down because our carbocation is now more stable, it's lower in energy, and so it would maybe look like this. It's going to be a little bit smaller of a hill. Now let's say that instead of a tertiary carbocation, let's say it's just a primary one, which would be really bad. Well, as we know, less substituted carbocations are more unstable, so that would be very high in energy. So maybe our hill, this is probably extreme, but our hill, right, our intermediate would be way higher in energy. And as you change how tall that hill is, that rate determining step, you're changing the energy of activation. So, just in conclusion, right, maybe I'm beating a dead horse, but I want to help you understand this if it's a little tricky for you. The more stable the carbocation, the smaller the hill, the faster it will go over. The more unstable the carbocation formed, the bigger the hill, and the longer it will take to go over, the harder it is, the higher energy of activation. Hopefully that helps. Okay, so with that in mind, let's come back to our question. And we want to compare in each of these reactions this step where we make the carbocation. This is going to be our rate determining step that will determine the speed of all these reactions. Okay, so starting with this one over here, we have a tertiary carbocation. This one has a tertiary carbocation as well. This one also forms a tertiary carbocation. This one, however, would form a secondary carbocation. And remember, right, we can't form the carbocation here because our double bond was here, so we can only put the positive charge here or here. And this is the better option. But a secondary carbocation is still more unstable than the rest of these. So that's why A is our answer as the one that will form the slowest. Okay? You can go ahead and skip along. If you're still not understanding this, I'll just re-emphasize once again. The formation of this one here might look something like this, where here's the carbocation we're forming, whereas the formation of this one over here it might look something like this. It's still the biggest hump to overcome, but not as big as this one. And once again, these don't accurately represent every step in this. I'm just trying to emphasize the formation of the carbocation.
Okay guys, this is going to be numbers 11 through 15 on the multiple choice. So first, it asks, which of the following statements regarding the addition of HX to alkenes is true? Well, first of all, we know that if we add HX or do hydrohalogenation of an alkene, that we are going to have this as the reaction mechanism. It'll first add, the hydrogen will add the less substituted carbon, forming this carbocation, and then the halide anion will attack that carbocation on both sides, okay, which will give us this product. And because it can attack on either side in this carbocation intermediate step, once we're going from the carbocation intermediate to our final product, we know that syn and anti are possible. Syn and anti addition are possible. So that means that we can get rid of B and C because it says that those happen exclusively, they're syn or anti. And the first one says that A says an achiral alkene yields a chiral product. So when an achiral alkene yields a chiral product, an unequal mixture of the two enantiomers is formed. So it says it's unequal, so that's false, because we know that whenever we have an achiral alkene or an optically inactive starting material and we're treating it with an optically inactive reagent like HX, that an optically inactive product must be formed. And if we have two enantiomers formed, that means that it's got to be an equal mixture in order to be optically inactive. So we're going to form a racemic mixture. And we know that because in this carbocation intermediate, it's got a trigonoplanar geometry, so it'll attack from the top and the bottom, so it could form both enantiomers in equal abundance. So we know that A, B, and C are wrong, so it leaves us D is the only correct answer. And that can occur when you have an optically active starting material, such as this alkene. Sorry, that's the alkene, double bond is here. Then you could form one diastereomer in greater abundance than the other. So for example, if we were to add HX to this, we could get different products, including these products. We have a cis cyclohexane ring, and then we have the anti. So this one here would probably be formed a little bit more than this one because there's less steric hindrance when you're attacking this carbocation that's formed. So number 12, it asks which reaction of an alkene proceeds exclusively with anti-addition. So we know hydroboration oxidation is syn only. We know that bromination, that's anti, okay? And we know that HBr addition is syn and anti, which is just what we did up there. In number 11, we wrote that. And we know that hydration is also going to be syn and anti. It's going to undergo basically the same mechanism as hydrohalogenation or the addition of HX to an alkene, except instead of having the halide anion attacking, it'll be water, and then you'll have water deprotonating the last step. So that leaves us with B is the only answer, because these are syn and anti, C and D, and A is syn only. And we know that bromination is anti only because we form that bridged halonium intermediate, and then a backside attack occurs at the more substituted carbon, and then that'll open it so it's only anti-addition. All right, so for number 13, it's asking us which set of reagents would work best in converting 2-methyl-2-hexene to 2-methyl-3-hexanol. So first of all, we're going to want to draw that out. So we have 2-methyl-2-hexene here, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, okay? And we're trying to convert it into 2-methyl 3-hexanol, so this. And we note that in this alkene, we see that the hydroxy group, the alcohol, is adding to the less substituted carbon. We're forming the less substituted alcohol. And there's only one reaction here that we know that will do that, and that's actually C. We know that the BH2 will add to the less substituted carbon because there's less steric hindrance when it's attacking that one in the addition step, and then this will just oxidize it to an alcohol. Also, to eliminate these answers, we know that when we're hydrating an alkene, we're going to form the more stable carbocation. So the hydrogens get added to the less substituted carbon, which would end up giving the more substituted alcohol. So that's not it. This HCl one, this would also yield the more substituted alcohol, as we'd initially form an alkyl halide with the chloride here, and then that would just leave and undergo an SN1 mechanism to form the more substituted alcohol as well. And then this one would form a halohydrin, which is not one of the options, so we know that D is wrong as well. So C is the correct answer. 14 is asking you to rank the compounds in order of decreasing basicity. So the most basic first. In this case, the only thing that's changing is the hybridization of the orbitals, and specifically we want to look at the lone pair. And we know that in this number 3, this lone pair, this is a sp3 hybridized carbon, has 4 groups, so it's going to be sp3 hybridized. So this lone pair is in an sp3 hybridized orbital, whereas in 2 it's in an sp2 hybridized orbital, and 1 it's in an sp orbital. So we know that this, the sp3 orbital, has the lowest percent s character, so it's going to be farthest from the nucleus. And that means this lone pair in 3 is going to be farthest from the nucleus and most available to deprotonate something, and thus most basic. Number 2 will be the next most basic, as it's in an sp2 hybridized orbital. And then number 1 is going to be the least basic because it's an sp orbital. So that means it's going to be closest to the nucleus because it has the highest percent s character in that orbital. So the correct answer is going to be 3, which is greater than 2, which is greater than 1. So these are all wrong. And number 15, it's asking you what compounds produced when one equivalent of HCl is added to 1 hexyne. So first, let's draw that out. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so that's 1 hexyne. And we know that when we add 1 equivalent to 1 hexyne, we form a vinyl halide. I'll draw that process for you here just to make it more clear. So this is going to be attacking the hydrogen there, cleaving this bond, while at the same time we have an HCl on the other side that's going to be cleaving and then attacking at the more substituted carbon. Okay, so what that's going to form is we're going to be forming this product. Let's see if I can draw that right. Yeah. Okay. So we'd be forming that product. We have 6 carbons, so the chloride is going to be adding to the more substituted carbon. And if we were to name this, we know we'd number the carbons like this from the side that gives the alkene the lowest number, and that would give us 2-chloro-1-hexene, which is A. So that's the correct answer.
Okay. So on number 16, we're asked which of the following can be formed as the intermediate of a hydroboration oxidation of an alkyne. So if we remember back, when we do hydroboration oxidation of an alkene, we're going to get a primary alcohol. So let's start thinking about that. So if I'm going to do hydroboration oxidation of an alkene and I get a primary alcohol, more than likely my intermediate is going to have a primary alcohol of some sort. So if we kind of look at the mechanism that's in the book on this one, if we do hydroboration oxidation, we're going to add a hydrogen to the side that's more substituted, and then we're going to be left with a less substituted oxygen or a less substituted alcohol, and then we're going to turn that into an aldehyde. So essentially we're trying to see which one's going to be the best one we can turn into an aldehyde. And the last step of the hydroboration oxidation mechanism is tautomerization. So if we look at these, is this really a primary alcohol? Am I going to be able to tautomerize this into an aldehyde? On this one, no, you wouldn't. That would be a ketone. That one as well would be a ketone, and that one as well would be a ketone. So realistically, the only one that makes sense following the mechanism of hydroboration oxidation, which is adding a primary alcohol or a less substituted alcohol, and then tautomerizing, would be A. So 17 says rank the following alkenes in order of increasing heat of hydrogenation. So when something's going to have an increasing heat of hydrogenation is something that's less stable. The less stable it is going to have a higher heat of hydrogenation. So we look at these, we have a di-substituted alkene, a di-substituted alkene, a mono-substituted alkene. So which one of these is the most stable? If we look at it and we think about it, the one that's going to be the most stable is the trans one. And the reason that the trans di-substituted alkene is the most stable is because we have no steric hindrance, as well as it is more substituted. So the least stable one is going to be the mono-substituted, and then it's going to be the cis is going to be right in the middle, and the cis is right in the middle because of steric hindrance, because of the two substituted groups on the same side, and then the most stable is going to be the trans. So from least stable to most stable, it's going to go 3, 1, 2, and then least stable has the higher heat of hydrogenation, so it's going to go 3, 1, 2, making it C, or 2, 1, 3. Okay. So what is the identity of compound Y? So we go into this one. When we react an alkyne with H2 and Lenoir's catalyst, what are we going to do? We're going to add syn hydrogens. Okay. So if we add syn hydrogens to this, we're going to be left with an alkene with hydrogens on one side. And then we're just going to halogenate it. So when we halogenate it, we can add it from one way that makes it easier for me to remember stereochemistry is we can, when we halogenate something, we're going to form a halonium ion. And you can add it like that. Or you could add it like and then we're going to perform an attack with Br. Okay. And so if we do it on this compound and we hit it with the bromine, it's going to open up either way. And so when we open up either way, we're going to get opposite. We're going to get a 2,3 RR or a 2S and a 3S. So we're going to have like a mix of enantiomers here. And so that's how it's going to be a racemic mixture. So it's just important to remember the stereochemistry involved with halogenation and that we are going to always have that mix of like stereocenters when we do it. Okay, so if we talk about 19, which of the following sequences will convert alcohol A into ketone B? So if we start with A, PCC, what's that going to turn this into? It's going to turn this into an aldehyde. Then we do LiLH4, then H2O. That's a reaction we generally learn with epoxides, but if you treat an aldehyde with LiLH, you're going to just turn it back into an alcohol. Polyl, pyridine, or pyridine, we're going to just dehydrate it. And so we're just going to have a double bond there. And then we're just going to make an epoxide. So our final product in this one would probably be an epoxide. So we could look at B, do polyl, pyridine. Okay, we have a double bond here now. MCPBA, we're going to have an epoxide here now. And then if we treat it like LiLH4, we're going to open it up and we're going to form a secondary alcohol. And with that secondary alcohol, we're going to treat it with PCC to oxidize it into a ketone. So it's important to remember we need to do an oxidation here to go from an alcohol to a ketone. But if I just oxidize this right here, I'm going to have an aldehyde. So I got to move this alcohol somehow over here to this carbon. So that's how we do it. If we do it with PBr3, that's going to put a bromine on the end. Okay. Then we have a double bond. Then BH3, then H2O. That's just going to give me literally my alcohol, my primary alcohol again, and that's just going to give me, okay, an aldehyde. We do that exact same thing. We have a double bond here. We halogenate it. NiNH2, 2 equivalents. Okay, we're going to NaNH2, 2 equivalents. Turn that into an alkyne. Okay, so we have an alkyne here. Then if we do an alkyne and just do that exact same thing, what are we going to get? We're going to get an aldehyde. So epoxide, ketone, aldehyde, aldehyde, and our thing is a ketone. So that's why that one's going to be. So which of the following are formed by ozonolysis of the compound below? So if we remember, ozonolysis is just molecular scissors. So if we do molecular scissors on this, we're going to cut these in half. I know I'm going to either have ketones or aldehydes depending on the substitutions of the carbons. So if I look at this one, I'm going to have an aldehyde right here because I have a hydrogen coming out right here. I'm going to have an aldehyde here, hydrogen coming right here. This one will be a ketone. This one will be an aldehyde because I don't have another carbon group coming off. So, okay, looking at this easily you can tell it would be 2 is going to be correct. I'm not just breaking it in half, I'm breaking it across both bonds. So I need something that's going to have my correct number of carbons. And so when we do ozonolysis, we just have to remember we have to stick with our same number of carbons. So we have 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 1, 2, 3, 4. So this one's going to make a 7. That combination is going to do 7. And then 3 is easily not going to be part of that.
Okay guys, this is Ryan. I'm here to do number 1 of the free response, which is predict the products. So the first part of number 1, we had this alkene, and we were treating it with H2SO4 and water. So we know in that case that the proton or the H hydrogen atom is going to add the less substituted carbon. So we'll go ahead and draw that. We know that an acid, let's just say we're using hydronium because we have water and sulfuric acid, so hydronium will be present. We're going to have this double bond is going to attack that hydrogen, and it's going to protonate the double bond, which is going to give us, let's draw it right here, it's going to give us this carbocation intermediate. Okay, and then what's going to happen next is we have this water, which is going to attack the carbocation, which will give us this product. I guess I'll draw it like that. And then we'll have a final deprotonation step where the water is going to come back in and deprotonate that, and it's going to give us our final product, which would be this tertiary alcohol. Okay. So hopefully that makes sense. That's number 1, or the first part, number 1. Next, we're going to have this epoxide, and we're treating it with strong acid. So we know that when we're treating an epoxide with strong acid, we're going to we're going to protonate first. Okay. So that's what's going to happen here. We got these lone pairs on this epoxide oxygen. It's going to get protonated by the hydrobromic acid, which is going to give us this product or intermediate. Okay, when we have that product, we have this Br minus that was booted off, and we know when we have a positively charged 3-membered ring, whether it's an epoxide, a protonated epoxide, or a halonium ion, bridged halonium ion, that the nucleophile is going to attack at the more substituted carbon. So that's what's going to happen here, and it's going to perform a backside attack, right? So this is going to attack here, breaking this bond, which is then going to give us this product. Since that was a dash, we're going to make it a wedge because it's attacking from the backside. And then this is going to be our Br, and our alcohol will be there. Okay, so that'll be the product for number 2, the part 2 of number 1. Okay, now we're going to hop on over to part 3 of number 1. Okay, so we have this cyclic alkene. And we're treating it with Br2 and H2O, so we automatically know we're going to be forming a halohydrin, okay? But we don't know which one's going to be which. So what's going to happen is we're going to have, I'll just draw the Br again here. What's going to happen is we've got our bromine here, and we've got this guy attacking the bromine, the pi bond, while the electrons on the bromine are going to be attacking there. and this bond is going to break at the same time, and that's going to form this compound. It could be either dashes or wedges here, although it's not really going to matter because this is not a stereocenter. We'll see that. So let's just say it's adding to the top of the pi bond. Okay. Then what we're going to have, and this should be positively charged. Since you have a positively charged sphenoid ring, we know that the nucleophile, which in this case is going to be water, is going to attack at the more substituted carbon, okay, which is going to then open that ring, and we're going to have this, although this is still an H on it, okay. So we still have this intermediate, and since it's positively charged, we're just going to have another water molecule come back in and deprotonate it, which is going to give us our final product, which is going to be the more substituted alcohol. Hopefully you can see that. That's kind of small, but that's going to be the final product. Okay, this halohydrin with the alcohol and the more substituted carbon. So that's going to be that. That's going to be product there. Okay, and that's that. And again, we don't need to draw any stereochemistry for this one because it's not a stereocenter. It's the same around, same on both sides, regardless of which direction you go around the ring. They're going to be the same. So these two groups are equivalent. So it's not a stereocenter. The same can be said here. No stereochemistry is necessary to draw because you have two methyl groups. So that makes so this carbon is not a stereocenter. Okay, now let's get on to the fourth part, which is going to be treating this, 1-butene with 2 equivalents of HCl. So I'm just going to go ahead and draw the mechanism for this. We know that both equivalents are involved in the first step. So this pi bond is going to be attacking the hydrogen atom, and its hydrogen is going to add to the less substituted carbon, sorry. And then this is going to be breaking at the same time, and this chloride is going to be attacking, which is going to give us our vinyl chloride intermediate, which will look like this. Okay, and then we know that we have our second equivalent of HCl, and then it's just going to be the same thing as a hydrohalogenation of an alkene. We're going to have the pi bond attack the HCl, which will give us this product. The carbocation is here. You can draw a second resonance structure of this. It's actually the major contributor, but in this case I'm just going to draw the remaining Cl minus chloride just attacking that carbocation. But you could draw a resonance stabilized carbocation, another resonance structure, because there's alone pairs adjacent to a carbocation, but this will get you the same answer, and we're going to get a geminal dihalide as our product. Okay, once that adds. So if that makes sense, let's hop on to the last two. Parts of number one. Okay guys, this is going to be the last two parts of number one. So first we had this product and we were treating it with hydrogen with a palladium catalyst. I guess plated with carbon, okay. And this one was treated with K2Cr2O7 with H2SO4 and water, okay. So this first one here is kind of that cartoony mechanism we learned about. And remember the problem was asking you to identify the major product formed. So we will get two products, but there's one that's definitely going to be a major product. Remember that in the addition of hydrogen to an alkene, so in the reduction of alkenes using hydrogen and a palladium catalyst, we're kind of on this metal palladium plate, okay? And we have the hydrogen atoms that kind of bind to it like this. They have this kind of cartoony mechanism like this, right? And then you had, I'm gonna try to draw this in 3D so it's not, okay? So you have this, and then in this case they tell us that we have a wedge coming out at us, right? So that means that the ideal way for this alkene, the hydrogen to add to this alkene, is with the wedge or the methyl group coming up like that, right? So let's just say this is our wedge. I'll just draw it as a wedge, but it's technically, yeah. So we're just going to draw it coming up. Okay, so we have our methyl group here, because that way we avoid the steric hindrance of this methyl group interacting with the plate. There's less steric hindrance, and it's easier for these hydrogens to add. So if the hydrogens add in this conformation, that means it's going to end up looking like this. If we draw it kind of saying we're looking at the alkene or the cyclopentane ring as if it's like flat like this and coming out at us like that. We know that it's going to, if the hydrogens will add this way because it's less sterically hindered there, so then you're going to have both methyls are going to be coming up, and then the hydrogens that we added will be here and here, okay, right, because we had 2 here already, okay, I guess those could be wedges and dashes if you want to, so that'd be a dash. Let me draw this better. This could be a wedge. Those are the hydrogens already there, and then we're going to be adding this one here, and then those original hydrogens will be up there, but we added these 2 hydrogens here. And it's better to be adding on the side that's less sterically hindered, so that's going to give us our major product, which will be this, with both of these as wedges. Okay. If that didn't make too much sense, I'd recommend going back to your book. It's kind of hard to draw these things in 3D, but this is kind of the mechanism we went over in class, where it's just kind of coordinating to this palladium catalyst, which is here, and then the hydrogens add to the bottom of the double bond, and that's how it works, okay? For this bottom one, we have, it's an oxidation reaction, so we're treating it with, we're treating this diol with a potassium dichromate and strong acid. So this is going to be the same mechanism that you have in number 4. So I'm just going to go ahead and draw, what happens with after the mechanism in number 4 occurs. After the mechanism in free response question number 4, you're going to end up with this. Okay. Although we know that if we were treating it with just PCC and CH2Cl2, then this would be the answer. But we're treating it with a really strong oxidant, right, which is potassium dichromate with strong acid. So this can still be oxidized more because we still have a hydrogen atom here, okay, coming off this carbon. So what we're going to do is we're going to have one intermediate step, and we're going to form what's called a hydrate. And that can just be formed because we know we have H2O and sulfuric acid, so that means there's going to be hydronium in solution from an acid-base reaction between the sulfuric acid and the water. Okay, so that's just going to go like this, which will form this intermediate, okay? And once we have this intermediate, we're going to go ahead and have this water attack here, which will give us this product. And then this water molecule will depronate that to give us our hydrate. And then we're going to perform this mechanism one more time from number 4, and then that's going to give us our final product, which is going to be a ketone with a carboxylic acid here. Okay. So that'll be your final product there, if you can see that. So that's it. So that's number 4 or number 1. If you have any questions, go ahead and ask one of your TAs.
Alright guys, let's look over number 2 of the free response. I'm going to do this one in a couple parts just because there are lots of parts to the question. So starting from the top, this first one, well, they all are asking us what reagents can we use to get from a certain reactant to a certain product. And some of them might require more than one step,
You need to specify if you're using more than one equivalent of something, etc., etc. You don't have to show reaction mechanisms on these. I will for some of them if it helps us understand how to get the right answer. Okay? So for this first one here, we're looking at how we can turn this alcohol into this alkyl halide. And if we look at it, they're really, really similar. The only functional group that's changing is this OH to this Br right here. There's not any wedges or dashes, so we're probably not going to need to worry about stereochemistry in this case. So looking at this, there's a couple different ways we could do it. We have to think, okay, do we know anything that takes us directly from an OH to a bromine? And the answer is yes, we do. We have PBr3. Okay. The other thing that you could do with this is you could add HBr. So PBr3, I'm not going to go through the whole mechanism. You can find it in the textbook. But it's going to turn this alcohol to a good leaving group, and then bromine comes in and does a substitution. With the HBr, the oxygen gets protonated by this hydrogen, and then it does a backside attack, an SN2 reaction. The bromine comes in and attacks this carbon, and then the water comes off. So hopefully it's okay, I'm not going through those. These are two different ways you could get this. There are other ways you could get this same product, but these are the two most direct ways to do it. So if you lost a point or so, and that goes with all of these, if you only got half credit, it's probably because there was a more direct way that you could have done it. Okay, looking at this next one. So, okay. I'll say with these, whenever we see wedges or dashes, we know that stereochemistry is probably going to be important, and it's something that we need to watch out for. So let's think about stereochemistry in this question. We're going from this alcohol to this right here that has cyanide substituted in. That's a pretty good hint to us that at some point we're going to want to add this into the reaction, and it's going to act as a nucleophile, because that's really the only way that we have used to get CN. And once again, we know that this is a strong nucleophile. It's got a negative charge. Okay. So, can we just add, right off the bat, let's just think, can we add this to get this? The answer is no. Why? If this were an alkyl halide, we could do a substitution, but it still wouldn't get us the right answer. We'll get to that in a minute. But this is not a good leaving group. A lot of what we've learned this unit is learning how to turn alcohol into good leaving groups so that we can react it with something else. So the way that the key shows this done is using TSOH first. And when we use TSOH, I'm not going to go through the mechanism once again, but it's basically just going to latch onto that oxygen, and it's going to turn that oxygen into a good leaving group. Now, a key thing with this, with using TSOH, there's several things that we know that could make this a good leaving group. For example, if we use PBr3 again, that would swap out the oxygen for a bromine, which is a good leaving group. However, the key to this one is, once again, thinking about stereochemistry. We know that when we add in our cyanide, which is a strong nucleophile, it's going to do, if it's an SN2 reaction, it's going to do a backside attack. So that means that, all right, this was the edge of our ring, and this is a good leaving group. Can you guys see that? Hopefully. If this is the edge of our ring and it's a good leaving group, we would know that we want this to be a wedge. So that way, when this attacks, it forms the dash. Okay? So that being said, we already have a wedge here. We want to preserve this wedge so that when we do a backside attack, it will get us this. And using TSOH, the special thing about TSOH is that it maintains the stereochemistry of the OH group. I don't don't remember exactly how to write it, sorry. But when we add the TSOH, it turns this into TSO, and it's got all this stuff on there. You can look at the mechanism, and it's going to maintain the stereochemistry. So then from there, now that this is a good leaving group, we can add in our cyanide, which is going to do a backside attack. Once again, think back to last unit. We've got a secondary, it's not an alkyl halide, but it's a secondary thing with a leaving group on it. We're attacking it with a strong nucleophile. Oops. Sorry. I want the dash here. Which is going to give us our product. Now maybe you thought, wait a minute, secondary thing with a good leaving group on it, we're using something that's a strong, sorry, just kidding, that's a strong nucleophile, not a strong base, so we don't have to worry about conflicting E2 reactions, okay? Now, the other way that maybe you might have done this, you might have done it in a way that would get you an SN1 reaction instead of an SN2 reaction. And if you did that, yes, maybe this would form, I guess, I don't know how that would happen because this is going to be a strong nucleophile. So, but if you did find a way to do it, this is a possible way to do it, and it's a lot more direct than doing it via SN1, because if you did SN1, you'd have competing E1 as well, and also you would get a mixture of the two different enantiomers, and so, or stereoisomers, diastereomers in this case. And so it's not going to work as well. So if you did it some way with an E1 or some other way that was a little bit less direct, you probably got partial credit on this one. Alright, so continuing on with the free response question 2. This one is the next one down on the list. So for this one, we didn't talk about the mechanism for how to do this, but you just had to memorize that when you have something like this with a sulfur and it's got a hydrogen on it, and you want to essentially mirror it, or you want to like double it, stick two of them together. You use BR2 or I2. So once again, we didn't talk about the mechanism for this or really how this works. You didn't need to know it, you just had to have this memorized. So this test was hard, there was a lot of memorization. This is one of those things, one of those reagents that you needed to have memorized. Okay, so moving on to this one. This is just getting rid of this halide here and leaving us with this alkyl halide. So we want to think to ourselves, do we know anything that can just take us directly from point A to point B? And the answer is yes. Okay, we can use LiAlH4, which we talked about looks like this. And the kind of strange thing we talked about with this molecule is that the hydrogens actually kind of own the electrons more than the aluminum in the middle, because they're more electronegative than the aluminum, which is kind of odd. So when these hydrogens are given up, lots of times when we look at things, like for example OH3+, and we say that the hydrogen gets deprotonated, and we say something like, okay, a base comes along and it's going to take one of these hydrogens, and then the electrons in that bond stay here with the oxygen to leave us with water. However, the unique thing about this molecule is that when the hydrogen goes somewhere, these electrons also come with it. So these electrons in the bond stay with the hydrogen and go as a hydride, or an H-. So that allows it to act like a nucleophile, because you have this hydrogen, it's got these electrons with it, and so what will happen is this will kind of do like a substitution reaction. I don't know if it's SN1 or SN2, but it doesn't matter that much. If it does, I'm sorry. But that hydrogen with its electrons are going to go in there, the chlorine will come off. And that will add that hydrogen to here. So here we have the chlorine and the hydrogen. After we add the hydrogen, the chlorine comes off. And you have the other hydrogen. This one, if I remember right, I don't think we talked about the mechanism for it too much. So it's okay if you just recognize that you can use this to reduce it to that. And the other thing I'll mention, the key shows this also adding water. That's just because we talked about this is a really kind of dangerous reagent and it's very, very flammable. It can explode easily. So you just want to use water with it to kind of dampen it down, the reactivity of it, so that it doesn't blow up in your face. So that's why the water's there. Once again, there are other ways you could have done this. You could have tried to maybe change this into a double bond and then reduce that from there. But this was the most direct way of doing it, just one step. Alright, so this is the last part of question 2 on the free response. So we're trying to get from this alkyne right here to these products. Okay, so we know that we want to be adding oxygens, OH groups onto this. We know a couple ways to add OHs onto a double bond or a triple bond, but in this case we preferably want to use something that's going to add 2 at the same time. And if we look, we see that these are both coming out of the page, these are both going into the page. So we know that we want to do a syn addition, adding both from the same side. So to do that, the best thing that we can probably use is OSO4, because that adds the 2 oxygens from the same side. However, before we can just react it with OSO4, we need to get rid of one of our bonds. Because if we were to add OSO4 to this, then we would almost get to the right answer, but we would still have this double bond in here. And then if we try to reduce this double bond after, it could mess with these OH groups, and it might not go as we hope that it would. So the best thing to do is to reduce this to a double bond first, and then react it with OSO4. Okay, so first we can react this with NaNH3, and that's going to reduce it from a triple bond to a double bond. And from there we can react it with OSO4 and the other reagents that come along with that. We can use NMO. And that's going to add, if you remember, that's the one that kind of looks like this. And so it's going to come in and add these 2 oxygens at the same time from one side. So here we have the 2 different products that result from this. In this case, if it was coming from the top, and in this case, if it was coming from the bottom. There's also another way you could do this that I think would have gotten you full points from what I've heard. And that is if first you used, I'll draw it up. So if at first you used H2 with the Lindlar catalyst, and what's special to remember about the Lindlar catalyst is it's going to reduce it, but it's going to leave the cis form of the alkene instead of the trans form. So that would get you this. And then from there, yeah, you could use MCPBA with H2O and H2SO4. And what you would be doing here is that would create, right, the epoxide ring, and then you would have your water coming in and attacking from the other side. And it would be an anti-addition, but because it's in the cis form, it would also end up getting you these two products. So if you didn't think of that, don't worry about it. The first option I went through is maybe a little bit more simple, but if you did that second option, that's okay as well.
Okay, question 3 on the free response was to draw this mechanism. So this is a chlorination or a halogenation mechanism. So the key part to this is to draw the intermediate correctly. If you were to draw this part, you need to draw the lone pairs that this would occur. This pops this off. This chlorine is going to have a more, it's going to have like a partial negative, whereas this one's going to have a partial positive. And that would look like this. Where you have the polonium intermediate. So that's the first step. If you did that, you got the first point. The second point was for then bringing in this chlorine that popped off with the negative charge. You can come in and attack here. I already drew an arrow. This will pop out, and you are left with the product. So you got half a point if you even just drew the product or an arrow to the product.
So as we go through this mechanism, it says draw an arrow pushing mechanism for the reaction shown below. To simplify your answer, you may draw the mechanism with CrO3 as an oxidant instead of PCC, and use base and an acid if you need a base or acid in the mechanism. Do not skip any steps. So most people got this one right. So what we're going to do is we have to come from our electrons, and we're going to have to come from our oxygen, and then we're going to attack the chromium, okay? Push the electrons onto that oxygen right there. And then we're going to come and we're actually going to protonate this oxygen right here, push the electrons back onto there. And then we're going to pull that hydrogen off by that base, push those electrons right there. And then you use the base again and just pull off that, make a double bond there, push those off and push those off, giving us our products. So the most important part is this proton transfer step. It's needed in the mechanism. Dr. Castle sent an email about it. If you did an intramolecular proton transfer, you got like 3.5 out of 4, I believe. So overall, this question just came down like memorizing mechanisms. And so we just got to remember we're going to, on a oxidation with CrO3, we're going to take that, remember that proton transfer step, pull it off right here, and then pull that, push those electrons right there. And so overall, guys, this was a really hard test. I just want to give you guys some words of encouragement. We still have like quite a significant amount of points left. There's still a 4th exam. There's still a final which is worth more points. So just finish strong. One of the most important things is if you don't know the answer on a test problem, just always write something out, because if you write something out, you're more than likely going to get at least half a point, maybe a point. And you know those points add up at the end of the day. So just keep finishing strong, work hard. You guys are doing great. Remember, this is a hard class, and just go easy on yourselves, but work hard, and you guys are going to be very successful. If you have any other questions, just reach out to us, any of us in this office hours. Thanks for watching this video. Bye.
All right, guys, let's look at number 5 from the free response. So this one was a very challenging question. It was the challenge question on the test, and it was tough, okay? So cut yourself some slack if you didn't get it right, but let's work through this together. So it shows us this big molecule right here. It says that we're going to be forming this compound. The only things that we can react it with are H2SO4 and H2O. So the question gives us a couple hints. One of the hints, it says hints. Number 1, number the carbons in the starting material to help determine their location in the product. So if we do that, it'll help us kind of see where these carbons are supposed to end up. And so I just numbered this, and this is what the key shows, just numbering this starting from left to right. And we didn't label these ones out here, just the ones along the main base change, the main backbone of the molecule. And then over here, we're showing those same carbons. So how do we know which carbon goes with which? Well, starting with carbon 1, we see that carbon 1 has an oxygen attached to it, and it's also got 2 methyl groups. Now, our oxygen, especially in this epoxide ring, is going to be pretty reactive, so there's a good chance that that could change and move somewhere else. However, methyl groups aren't very reactive, they're just carbons and hydrogens. So it's likely that they're going to stay attached to that same carbon 1 right there. So knowing that, we can look over here, and we see that right here there's these same 2 methyl groups attached. So we can assume that this right here is carbon number 1. So there's carbon 1. Then we wonder, okay, do we want to go this way or this way? A couple hints. This carbon 2 right here has an oxygen attached to it, which corresponds to the oxygen 2 over here. Also has this oxygen on it. The other thing that we see is if we count going this way, we'll hit carbon number 5 right here. Carbon number 5 here has a methyl group on it, and it does right here as well. So those are some hints that we can use to know we're going to start at carbon 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10. I labeled it all the way to 12. The key just shows it going to 10, but we can also see how these carbons right here, 10, 11, 12, are going to end up on this ketone right here. Okay, so now that we've got this numbered, it gives us another hint that we can look at in the problem. It says, hint number 2, are alkenes and alkynes nucleophiles or electrophiles? Answering this question will help you. So thinking about alkenes and alkynes, are these nucleophiles or electrophiles? Remember that nucleophiles are things like OH minus, for example. And nucleophiles have electron density that they can donate. They have electrons to give. Electrophiles are things that want electrons. Remember that with alkenes and alkynes, the double and triple bonds, they're just more electrons in those bonds. And so these can be considered to be nucleophiles. There are some practice questions in the homework, maybe some challenge questions, that show this kind of thing of double and triple bonds acting as nucleophiles. Or we have some reactions that we've used as well that show a double bond being used as a nucleophile. So knowing that those are nucleophiles, we see here we've got a double bond and a triple bond, both of which could be used as nucleophiles. Now we don't have any like alkyl halides where we can say, okay, we're going to use our nucleophile to attack right there. But what we do have is our epoxide ring that we can attack it with. And we know that since we're forming 2 rings, we have to at some point form 2 carbon-carbon bonds. And the epoxide ring is a great way to start because opening an epoxide ring with carbons is one of the only ways that we know to connect 2 carbons together. So looking at this, both of these, well, if we were to use this as our nucleophile to attack the ring, it's not going to get us where we want to go. And if we were to try doing that, you could maybe get down the path a couple steps and then realize that it's not going to work out. Using this double bond here is going to work out, and it's going to give us one of these 6-membered rings that we need. So if we had a strong nucleophile, like let's say we had OH minus. OH minus would be capable of opening the epoxide ring as it is right now because it's a strong nucleophile. However, our double bond here, it doesn't have a negative charge. It's not a very strong nucleophile. And so before it can attack the ring, we need to protonate our epoxide. So we can grab one of the hydrogens from H2SO4 to protonate this. Which will get us to here. Then from here, now our double bond connects as a nucleophile. We have to ask ourselves, which side of the epoxide ring is it going to attack? So a couple hints with this. If it were to attack right here, then we would have this kind of group sticking out. So let's say that this is our ring right here. We would have this group sticking out like an isopropyl group that's got 3 carbons, but we don't see that anywhere in our product. So that's one hint. But the other thing is that we learned that when we have a protonated epoxide ring, the nucleophile is going to attack the more substituted side. And that's because, we don't have to go into this super deeply, but if you think back, we talked about how this being protonated, once it's protonated, it starts to open by itself a little bit. And so that's going to place a partial positive charge from where the bond is breaking. And that partial positive charge is going to want to be on the more substituted carbon to be more stable. This is when we talk about like the SN 1.5 or the SN 1.5. So you don't have to think of all that, just reminding you as to why this attacks the more substituted carbon. So that's going to start to break. This double bond is going to come in and act as our nucleophile. And that will get us to here. Okay, I gave myself a minute to draw it out. So when this attacks over on this side, right, this bond is breaking, we'll get this over here. Now you might be wondering, how the heck did we get that? Once again, remember that we have this to kind of base ourselves off of. So when we show that connection coming over here, it's probably helpful to draw it in a similar orientation to how the product is oriented, if that makes sense. And the way that I would think of this is, remember, try to match up your carbons, okay? So we're trying to get from this to something that looks more like our final product. And in our final product, these 2 methyl groups, like the ones that are sticking out from our epoxide ring right here, they're pointing down. And some other maybe landmarks, I guess we could call them, is we have on carbon 5 this methyl group, which is also found right here. And this shows it in the product on the paper, shows it oriented going up. So let's try to match that orientation. And if we know that this is carbon 5, as we're calling it, with this methyl group, that would be this one right here. And so the one to the left of carbon 5 is going to be the one on top. So carbon 4 right there is this one. So you can picture this, to get to this orientation, I would picture it as you have carbon 4 as kind of like your pivot point, and you're taking these 2 ends and kind of swinging them down together. So imagine rotating around these bonds, swinging these down, you're bringing this carbon here down, this coming down to form this 6-membered ring right here. I know it's kind of hard to visualize, but try to picture it that way, as it's swinging down and around like that. We can double check from here if we wanted to, right? Make sure that we have the right spacing, that our carbon with the 2 methyl groups is right next to our oxygen, that's 1, 2, 3, 4 away from where our methyl group is, or 1, 2 in that direction. Check all these things, make sure that we're on the right track. Okay, so from here, now once again we have another alkyne, and like the hint says, alkynes and alkenes can be used as nucleophiles. That's what we're going to do again right here. So in this case, we have a good electrophile, this positive charge. We know anytime that we form a positive carbocation, it's going to be really reactive. It wants to react. So this positive charge wants electrons, and there's plenty of electrons in abundance right here in our alkyne. So what's going to happen is the electrons from the alkyne are going to go to the positive charge, to the carbocation. Now, also, the key shows this happening in 1 step. I'm going to show it happening in 2 steps. It's just as valid as if you show it in 2 steps, and I think it's a little bit easier to see. So once that forms there, let's redraw this once again. Okay, so we're just going to show the connection there, and you might wonder, well, which carbon is going to add? Is it going to come from this carbon right here, or from this carbon right here? Once again, we'll look at our product to see which one will make the most sense. So if we're connecting these two right here, that's going to be this spot. We know that we want one carbon, two carbons. We want two carbons to be coming off on that little leg. If we connect it right here, then we'll only have this one carbon sticking off. So we're going to have to connect it from this carbon right here. Sorry, right here. We're going to have to connect it from this carbon right here, because that'll leave one carbon, two carbons sticking off on the edge, if that makes sense. So we're coming from this carbon to that carbon, which will get us right here, okay? So notice how when we take away one of these triple bonds, this carbon right here, hopefully you guys can see that, hopefully it's not too small. This carbon right here, it's losing a double bond, or sorry, it's losing a pi bond, but it's making a new bond with this carbon. This carbon, however, this one right here, it's losing one of its pi bonds, and it's not getting anything else. So all that's happening, it's losing a pi bond, it's not getting anything else. That's going to leave it with a positive charge right here. So once that positive charge is there, then a water can come in and attack the positive charge. So remember, water is one of our reagents, and that will get us to this next step. Something I forgot to mention as well is that this methyl group here, when we fuse this ring together, it's going to come up out of the page. You might wonder, how would I know that that's going to happen? Well, we know that right here, this is in trigonal planar geometry, because there's only three groups attached to this carbon. So it could come from the top, could come from the bottom, but the product specifies that it is a methyl group, sorry, it is a wedge coming out of the page, so we know it's going to be wedged just because that's how it is in the product. I'm going to redraw this a little bit bigger, erase some of the board to give us some more room to go through the next part of this reaction. Okay, now we've got a little bit more room on the board. So if you remember, we left off right here with this step. And like I mentioned, I showed this happening in two steps. The key shows this water attacking in the same step that the alkyne goes to the positive charge that was here. So either way works. I just think this is a little bit easier to see it. Okay, so now once we get to this step, we've got our oxygen with two hydrogens. It's got a positive charge, so we're going to want to deprotonate. To do that, we can use water, or we can use the conjugate base of H2SO4, or strong acid. It doesn't really matter. I'm going to use water in this case. Okay, and something else I'll mention, it was really important for this mechanism that you were supposed to draw of including all your arrows, your positive charges. So if you missed an arrow or a positive charge here and there, you would have been docked a couple points, maybe a half point for each charge or something that you forgot. So just keep that in mind. Okay, so from here, we now have an oxygen and at its base is a double bond, which is called an enol. Whenever we have an enol, we know that it's going to automatically undergo a tautomerization. Okay? So first thing that's going to happen either our strong acid or water being activated by our strong acid, either way, is going to protonate this double bond here. And then also, the electrons up here on this oxygen are going to kick down to form a double bond here in its place. I'm just going to, if it's alright, I'm just going to draw the right half of the molecule because now everything on the left half isn't going to change. Camera died, so we had to adjust the angle a little bit, but picking up where we left off, we get from there. So okay, this double bond is going to be protonated, and then these electrons will swing down to fill in the empty orbital right here on this carbon. So that will get us to here, which has a positive charge, because this oxygen now has 1, 2, 3 bonds on it, and it has a lone pair. So from there, we'll use a base, something like water, to deprotonate this hydrogen, and then the electrons in that bond will end up on this oxygen. And that will get us here to our final product, where we have this ketone right here is what's being formed in this step. So once again, this one was very tricky. Try to practice this a couple times, see if you can do that tricky step where you have to draw the first ring forming. That's probably one of the hardest parts, but you guys got this.
All right, the synthesis problem. Last question that we have. So, when I do synthesis problems, I try and think of how can I get those carbons into the chain. So the question, you can use any starting material with an alcohol of 4 carbons or less. So in this, we have 1, 2, 3, 4, 5, 6 carbons. So I'm going to think, what can I do to add carbons to this chain? What different functional groups do I see? I see this ketone. So if I just break it up to, let's see, these 3 carbons here and these 3 carbons here, then it seems a lot more manageable to me. Because I can make that, and I can make that, and I just combine them, right? So what do we know that will make this? Well, if you have an alcohol, and you react that with an oxidizing agent, then it converts it to a ketone. So we have some reaction to make that. What about to make this? Well, if you dehydrate an alcohol, that would make the alkene. But then you have to think, okay, well, what can I do to actually combine these? So if you had an acetylide ion or an alkyne, which are commonly used in synthesis, then I could just reduce it to the alkene, combine these two things, and we'd be good to go. So I'm thinking, okay, I'm probably going to need an acetylide ion with 3 carbons. That would give me 3 carbons here, 3 carbons here. But the problem that I would run into, and this is a common mistake made in the synthesis problems, is thinking that you can react this with maybe something like this with a leaving group, right? But if you had this alcohol with the leaving group, it would not do the SN2 reaction. What it would do is it would deprotonate the alcohol. So we need to make this alcohol in a different way. So I'm thinking, okay, here is my alkyne that I'm probably going to need. I need the alcohol, but what is a different way that I could make it? And the answer would be an epoxide. If you were to react this acetylide ion with an epoxide, it could open up, you can make the alcohol, and then you can do it. So that is my thought process when I'm doing these synthesis problems. I don't necessarily write out everything backwards, but I think of what different things can I use here to just kind of break it down and make it easier. So, all right, let's start by trying to make this epoxide. So if we used this alcohol and we reacted it, or let's say we got rid of it. So let's use the one that he used. So you can dehydrate it a number of different ways, but if you do it with this, you're left with this alkene, which you can react with MC this we're gonna label as A because we're gonna come back to it. So we have this epoxide labeled as A. Okay, now we're gonna have to make this other side. So if you have, once again, let's just start with that same alcohol. Let's dehydrate it or eliminate it. We're left with this. We can't make this directly into an alkyne, but what we can do is we can halogenate it. That would make it like this. And then from here, you can make it into an alkyne by using NaNH2 2 times. So this first equivalent of the NaNH2 would knock off one of the bromines. You'd be left with an alkene with a bromine. The second equivalent will knock it off again, leave you with this alkyne. So that's kind of why you need the 2 equivalents. So we'll put those back on. Okay, you react with this. Now you have this alkyne. Okay. So this alkyne, to become reactive, it needs to once again be reacted with NaH or NaNH2 to take off the hydrogen here on the end and make the acetylite ion, which can react as a nucleophile. So this last equivalent of NaNH2 will take off this hydrogen that's right here and put that lone pair here and make the acetylite ion. Okay, so now we made what we needed, what we were thinking about in the beginning. We made this acetylite ion, we made this epoxide. So now we need to put them together. So we'll label this as B. So if we reacted this epoxide with the acetylite ion, that would react here and open it up. Then you would need to protonate it. So we'll say acetylite ion 1, protonate it 2, and then we'll go from there. So you're left with this. This hydrogen came from the water. Okay. So from here we still have we now have the correct number of carbons. We have 1, 2, 3, 4, 5, 6. We got all 6 carbons that we need here. And what we want to do is get it to here. So if we were to convert this down to this alkene, what you would do is you would use, if you were to use a Lindlar catalyst, this would make it cis, but we want it to be trans, so we're going to use something like NaNH3. That'll convert that to this in the trans form. And then all we have left is to convert this alcohol to a ketone, which you can do with any oxidizing agent. So like PCC or any of the chromium reagents, and there you have the product. So that is the synthesis problem.